Analyzing the amplified DNA is the next stage. So you can see that the DNA that is amplified in a PCR machine, and that after the thermal cycling, the tubes are taken out from the machine, and the contents of the tubes are loaded onto an agarose gel. The DNA is separated by size using an electric field. There's a gel electrophoresis is done. The DNA is then stained and visualized. Then PCR products are visible as different bands in the gel. So this is how we are visualizing the products of the PCR. So this is the electrophoresis unit into which you will load the samples on the wells, and by applying the current, here is the negative terminal, this is the positive terminal. The negative charge DNA will move to the positive terminal. So it will move down. The strands will be separated, or the DNA fragments will be separated based on the size. So gel is running, they will separate based on the size. And after the gel run, it is stained to reveal the DNA bands. Or it may not be stained. Usually, if we are labeling it with ethylene bromide, then you can visualize it using some instruments like UV transilluminator or a gel documentation system, in which these fluorescent dye will give the DNA, the bands a fluorescent color. So the bands will glow in UV light. The final result of the traditional PCR procedure is a gel with a series of bands. So this is the molecular marker run along the gel, so that you can identify the molecular weight of the products that is obtained in each and every sample. So this is the different samples from the wells, and based on the molecular weight, it will separate and resolve in the gel. The bands can be compared against each other and to known size standards. This is the ladder or the non-size standard. By comparison, you can find the molecular weight of the bands. To determine the presence or absence of a specific amplification product, you have to locate. For example, if your primary specific for a particular size product, for example, 500 base pair products, then you have to look for the product that is coming in that range. Maybe or this is a 600 base pair product. If your product is a 600 base pair product based on the primer length, then you can easily locate this is the concerned target gene. So the discovery and history of the Taq polymerase is again shown there. The original report of this enzyme is about that is purified from the hot springs of bacterium Thermus aquaticus, was published in 1976. Roughly 10 years later, the polymerase chain reaction was discovered, and shortly thereafter, Taq becomes, as in 1988, the Taq was started to use in PCR reaction. Standard was developed, and shortly thereafter, Taq became household word in molecular biology circles. And then scientists isolated the thermostable DNA polymerase Taq, an enzyme that drives PCR from Thermus aquaticus, Yellowstone type 1. This is already discussed in one of the previous slides. And a resident of the this Thermus aquaticus is a resident of the geysers like this one in the Yellowstone National Park. So this is a hot spring in the Yellowstone National Park, and this Thermus aquaticus was isolated from that Yellowstone National Park. The first isolated, it is first isolated from the bacterial thermophile Thermocarticus, and the Taq polymerase has become the staple enzyme in molecular biology. The commercial producers have since cloned and expressed these enzyme in E. coli. So it is not nowadays cloned from, just obtained from the Thermus aquaticus. The original gene was obtained from Thermus aquaticus, but now the commercial products were actually cloned products from E. coli. The concerned Thermus aquaticus gene was cloned in E. coli, and now it is expressed. The recombinant Taq is about 94 kDa enzyme, and with an optimal 5' to 3' polymerase activity between 75 to 80 degrees Celsius, and in the presence of a magnesium cofactor. So that's the enzyme nowadays used, which is a cloned product or recombinant product from E. coli. At 72 degrees Celsius, it can replicate the DNA strand for 1000 base pairs in less than 10 seconds. So Thermus aquaticus can produce a copy of the DNA up to 1000 base per length. So this cannot be used for maybe for amplification of the larger fragments like 25,000 base pairs or 50,000 base pairs. If your intention is amplification of the larger fragments or an entire gene, then you may require some other polymerase. So the amplification length, overall the product length of maximum product length of Taq polymerase is minimal. Taq lacks 3' to 5' exonuclease activity and is prone to errors at a rate of about 1 per 3700 bases. Aside from PCR, Taq is also widely used in TA cloning due to its ability to leave a 3' overhang. For example, there is a T at the end of the PCR product, and these are a DNA insert with an A overhang can easily be joined with the PCR product. So this TA cloning is actually one of the method of cloning. So this is the PCR product insert with the A, and this is the vector with the T. So this can be cloned. Some commercial modifications to consider include high fidelity with the recombinant addition of a 3' to 5' proofreading activity and a hot start feature to reduce these non-specific amplifications. So these are some of the commercial modifications of the Taq polymerase. These thermophilic DNA polymerases, like other DNA polymerases, catalyze the template directed synthesis of the DNA from nucleotide triphosphates. And a primer having a free 3' hydroxyl is required to initiate the synthesis. They always require a primer. Magnesium ions is necessary, and in general, they have a maximal catalytic activity at 75 to 80 degrees Celsius. That's the extension temperature, and substantially reduces the activity at lower temperatures. So the maximum polymerization activity or catalytic activity is at 75 to 85 degrees Celsius. Usually we are using 72 for Taq polymerase. And 35 degrees Celsius Taq polymerase has only about 10% of its maximal activity. So it is inefficient at normal room temperatures or normal temperatures. The recombinant Taq DNA polymerase is the enzyme of choice for most PCR applications, and the half-life of the enzyme is it's less than 40, and the half-life of the enzyme is less than 40 minutes at 95 degrees Celsius, and the error rate of the Taq DNA polymerase is about 2.2 into 10 raised to 5 errors per nucleotide per cycle. So that is the error rate of the Taq polymerase. It's not error prone, but it's error free. Some possibilities of errors are there. That the accuracy of the Taq polymerase can be stated something like this: 2.2 into 10 raised to 5 errors can be expected per nucleotide per cycle. So the other thermostable polymerases are PFU from Pyrococcus furiosus, Vent, that is from Thermococcus nitralis. So these are some of the other polymerases, and the other two is having 3' to 5' exonuclease activity. One of the most discussed characteristics of thermostable polymerases is their error rate. Error rate are measured using several different assays, and as a result, estimates of error rates vary, particularly when the assays are performed at different labs. So error rate is a significant factor when we are considering the quality of the polymerase. So the error rate, PFU appears to have lowest error rate, roughly 1.5 into 10 raised to 6, compared to 2 into 10 raised to 5 of a Taq polymerase. So the Ven polymerase is actually in between Taq and PFU. So the accuracy is more for PFU and low for Taq. Average error rate that is the mutation frequency per base pair per duplication is shown there. So PFU is the accuracy is much high when you are comparing it with the Taq. So amplification accuracy is much high. That's 1.3 into 10 raised to minus 6 for a PFU. And in case of a deep vent polymerase, it is 2.7 into 10 raised to minus 6. It's still high. So there are different polymerases, and here Taq polymerase, it is a 8 into 10 raised to minus 6. So comparatively, PFU polymerase is having the highest accuracy. Okay, thank you.